Good afternoon, everyone, and thank you for joining our webinar on energy transition and the role of energy storage with Eaton. My name is VM Melki. I'm the marketing coordinator at Rexel. Our guest speaker today is Richard Molloy, Eaton Business Development Manager, Energy Storage and Energy Transition, who will be introducing himself shortly. Please note, this is a recorded webinar and will be available to watch on demand on our Rexel website. This webinar is CPD accredited. Certificates will be sent to you directly from CPD, which can take 4 to 5 weeks. If you have any questions throughout the webinar, please feel free to put them in the Q&A box, and we will answer them at the very end. Now passing over to Richard from Eaton.
Okay, thank you very much. Good morning, ladies and gentlemen. Yeah, my name is Richard Molloy, Business Development Manager for Battery Energy Storage. I've been with Eaton now for just over 27 years. The last 6 or 7 years I've been directly involved in battery energy storage, EV charging infrastructure and building energy management systems. So welcome to this webinar. The title of the webinar is Energy Transition and the Role of Energy Storage. So before we get into the core subject matter, just a very brief introduction to Eaton. I'm sure many of you are very familiar with Eaton, who we are and what we do, but for those who may not be, just a very brief introduction. So Eaton are a power management business, and we aim to improve the quality of life and the environment through the use of power management technologies and the associated services. So our aim is really to help our customers use power, and that's power in all its forms, more safely, more sustainably, more economically, more reliably, and more securely. We're a global corporation. We operate in over 170 countries around the world, employ almost 100,000 people, and last year had a global turnover of just under $21 billion US. On the slide there, you can see our various regional headquarters around the world. So the overall business headquarters is in Dublin in Ireland, and we're affiliated in EMEA with the EMEA headquarters in Morges in Switzerland. This slide's just giving a few thumbnails of a range of the different market sectors that we operate in. I'm not going to go through each one of these, but I just want to pick out 2 or 3 that I think are salient to the core topic that we're talking about today. So the first one to mention is data centers. And the reason I mention that is we're a leading provider of uninterruptible power supply systems, UPSs, to the some of the world's largest data center operators such as Google, Facebook, Microsoft, and so on. And the reason I mention that is because, of course, the UPS system takes AC power, converts it to DC, charges and manages a battery, and then reconverts it back to AC to support a load. And that's the same core technology that you would use in a battery energy storage system. So we have sort of deep expertise in that power conversion and battery management technology. The next one to mention is renewables. Obviously, that's front and center stage of the energy transition. And whilst as Eaton, we don't manufacture complete wind turbines or complete PV inverters or solar panels, we do supply a lot of the OEMs of that equipment with components that go into those products. So for example, in a wind turbine, we do hydraulic pitch and yaw control systems for the blades. We do the transformers and the switch gear that sits in the base of the turbine, and all sorts of control and automation equipment that would sit within a wind turbine. And then the final one I just wanted to draw out here was the utility segment. And the reason I mentioned that is, of course, as we electrify all of our energy demand, then that's going to place a much greater emphasis on the role of the utility infrastructure, and we start to see smart grids and smart controls happening as we move power from where it's generated to where it's consumed. So that's all I'm going to say about Eaton. So move on to the core topic, which is energy transition and the role of energy storage. This is a CPD certified presentation. This was prepared a couple of years ago. I haven't changed any of the slides before, just to maintain the CPD certification. So there are 1 or 2 bits which perhaps are slightly out of date, but I'll call those out as we go through and mention what's what. So the topics that we're going to cover, first of all, we'll just have a little brief recap on climate change. I'm sure it's something that most of you are very familiar with. You know, not a day goes by without it being in the news these days. But we'll just have a brief recap on some of the history of where, you know, how we've got where we are. We'll then talk about energy transition and some of the changes we expect to see energy transition driving within our electrical system. And we'll talk about the impact of those changes, particularly on reducing system inertia and the effect that has on our ability to manage the stability of grid frequency. We'll then move on to look at some of the solutions to some of the issues we identify there, and particularly looking into sources of energy flexibility, and then focus in specifically on energy storage, not just battery energy storage, although we will move on to focus on that in a little bit more detail. And then finally, just sort of draw it all together, talking about how we can use battery energy storage to help us integrate electric vehicle chargers in our built environment. Okay, so this is considering some of the key trends we see in the energy sector. And over the long term, we've seen the price of electricity to continue to rise. And we're showing here a 50% increase from 2010. This is one of the things that perhaps needs updating. It was accurate when this was prepared in 2020, but clearly we've seen some fairly dramatic changes in the energy markets over the last year or two, driven really by the sort of the current global geopolitical situation. And we have seen prices drop back a little, but they've started to go back up again a bit now with what's been going on in the world. And certainly bills are very much higher than they were before the Russian invasion of Ukraine, which has really driven that price increases that we've seen for both residential and commercial consumers. During that same period, we've seen a big reduction in price of lithium-ion batteries as well, and the price reduction of 85% over that period. So that's really started to make the financials and the business case look very much stronger for battery energy storage systems. And the cost of installing renewables has also fallen very dramatically. And we now see it's cheaper to build new wind and solar resources than it is to build new coal and gas plants in most places in the world. And we're even seeing situations where it can be cheaper to build new renewable resources than it is to continue purchasing power from existing fossil fuel resources. And so we now see renewables producing more of our total energy demand, really around the world, but particularly in the UK. We're seeing the renewable share of our grid electricity mix really increase and become more and more dominant. So a little bit of a history lesson on climate change now. First sort of critical step in addressing climate change was made with the agreement in the Kyoto Protocol, which was agreed in 1997 and implemented in 2005. And at the Kyoto Protocol, it was agreed to reduce the emission of all sorts of greenhouse gases, particularly carbon dioxide. But there was quite a wide range of greenhouse gases which were identified in the Kyoto Protocol, and they were indexed against carbon dioxide. So carbon dioxide was given a global warming potential of 1. So 1 kilogram of carbon dioxide had a defined effect on the warming of the atmosphere. And then all of the other gases were benchmarked against that. The most aggressive gas was a gas called sulfur hexafluoride, or is a gas called sulfur hexafluoride, or SF6, which has a global warming potential which is 25,200 times greater than carbon dioxide. And I mention that gas in particular because that's the gas that's often used as the insulation medium in medium and high voltage electrical switchgear. So it is incumbent upon industry to decarbonise switchgear and to produce SF6 free 11 kV, 33 kV and higher voltage pieces of switchgear, which Eaton have been manufacturing for well over 60 years now, and other manufacturers have also started to bring out SF6 free alternatives. The next key step was the Paris Agreement in 2015. So that really was a landmark, a major step forward in efforts to combat climate change. And at COP21, all nations agreed to keep the increasing global temperatures to, and the phrase used was well below 2 degrees centigrade above pre-industrial levels, and to pursue efforts to limit the increase to 1.5 degrees centigrade. Clearly, we're seeing stronger evidence emerge almost on a daily basis for the imperative to target even deeper cuts. And it's also quite clear that we are quite a long way behind where we need to be to manage that increasing global temperature. And again, there's reports globally of significant weather events occurring and other impacts of climate change, making it very, very visible. And it really underlining the necessity to redouble our efforts to manage those emissions. And we have seen the planet warming by 0.2 degrees centigrade per decade, and I think that the warming, according to more recent media reports, is accelerating. So again, just really emphasize that point. We do still have, despite some, shall we say, political wavering of recent weeks and months, we do still have the net zero target in place for 2050. So we need to do everything we can to achieve that. So this slide is looking at some of the key drivers for energy transition, and clearly mitigating climate change is all about decarbonisation. And one of the key ways we can decarbonise our power system is to electrify everything. And that's a range of technologies, particularly electrification of transport. We see that happening at pace. More and more of us are adopting electric vehicles. We're seeing pure battery electric vehicles increase in size, so we're seeing a lot more light and even some larger commercial battery electric vehicles. We've also an imperative to decarbonise heat. So instead of using typically gas for fossil-fired gas for space heating, moving to electrified forms of space heating. So, for example, heat pumps and electric boilers. I think we're much further behind the curve on that journey, so that needs to accelerate. And we also talk about the electrification of industrial processes. So again, moving away from fossil fuel sources. An example might be a gas oven converting to an electric arc furnace. The next key pillar that we see is decentralization. And this is the move from a small number of centralized electricity generation resources to a decentralized model where we see power generation and energy storage being connected throughout the transmission and distribution system, and even what we call behind the meter in our homes and businesses. And we'll talk about that in a little bit more detail in a few minutes. And then the third one, and absolutely key, is digitalization. And this is absolutely imperative to enable us to operate and manage all of those distributed energy resources from that decentralization we discussed. And of course, this includes the digitalization of some of the key technologies that we use in the energy system. So things like smart meters, smart sensors, all of the control of that behind the meter generation, the flexible loads that we have. And of course, we're all adopting more and more what's generally termed IoT devices. So we're seeing connected fridge freezers and dishwashers and all sorts. So that digitalization piece really becomes much more critical to the energy transition. This is trying to quantify the scale of some of the forthcoming changes we expect to see in the energy system. And these numbers come from a report that was authored by Bloomberg New Energy Finance. And here we see an expected increase in building energy demand of 50% by 2050. And much faster than that, by 2030, we expect to see a 27% increase in total global electricity demand, driven purely by the electrification of transport. And we also expect a fourfold increase in the energy consumed by data centers for data and computing applications. Just interesting fact of the day, today, data center energy consumption is the same as the energy consumed by global aviation. So a huge amount of energy that's used for managing data, and we expect a fourfold increase in that. So clearly all of this electrification is going to demand a much greater supply of electricity, and equally clearly that electricity can't come from fossil fuel resources. It has to come from clean energy resources, the majority of which will be renewables. And so we expect to see 50% of our energy generation coming from renewables by 2035. That deep penetration of renewables into the electricity mix will drive a significant demand for an increase in flexible energy capabilities. And so that's going to drive a 13-fold increase in the amount of energy storage that we see connected to the grid. And all of those sort of fairly significant changes will have some impact on our infrastructure. We expect to see actually a reduction in system resilience as we go through this change. we expect to have 13 billion devices connected to the power system by 2025. So we need to use that digitalization to optimize all of those different resources. And of course, with that digitalization comes some very key cybersecurity risks. So we need to manage security, and that's one of Eaton's key promises, to go above and beyond the sort of minimum security standards. So cybersecurity is something where we have the highest rigor in all of our products and services to ensure that we prevent data breaches and problems with malicious actors in the data system. Here we're illustrating the decentralization of the power system that I spoke about earlier. So historically, we had a relatively small number of very large power stations. That power was generated and then transported unidirectionally across the transmission network, through the distribution network, and on into our homes and businesses where we consume that power. But over the last 10, maybe 15 years, we've seen a huge proliferation in decentralized generation. Sometimes at utility scale, sort of tens and hundreds of megawatts connected directly to the transmission system, but the vast majority connected either to the distribution system at 11 or 33,000 volts, or even in our homes and businesses at 230 or 400 volts. So that decentralized generation now starts to lead to the power flows on the system becoming bi-directional. So instead of flowing just one way from central generation to the point of consumption, we're seeing power flows moving around the system. And when we consider sort of the exponential growth in all of the connected devices, and as I've mentioned, that of course includes all the metering, monitoring, control of the power system itself, we can start to see a much more complex grid architecture evolve, and the data part becomes absolutely key. And this is something that at Eaton we describe as everything as a grid, and we can see sort of the flows, not just the flows of the power, but the flows of the data moving two ways across the system. So we discussed how we're going to see a huge growth in demand for electricity as we electrify. And of course, that energy has to come from renewable resources, and the majority of that will be wind and solar. And these technologies, of course, have quite different characteristics to conventional generation. And that brings some challenges for the system operators when they try to integrate that into the electricity supply mix. Because of course, a generator that relies on wind and solar will have a variable power output that will change in proportion to the underlying renewable energy resource. So in other words, is the wind blowing or the sun shining? And so that brings some challenges in terms of maintaining security of supply and managing volatility in both the actual system itself, technically, but also in the price of energy. We see huge swings in the market price of energy. And we're starting to see some fairly sort of innovative tariffs come out, certainly in the residential sector, which start to take advantage of that and start to reward people for consuming power when there are abundant renewables available. And conversely, that power is more expensive when the renewables are scarce. So that variability in supply of electricity does challenge grid operators to manage imbalances in generation and demand, and they have to match generation and demand in real time. So there is always as much energy supplied onto the system as there is drawn off it. So they have to manage those disturbances, and they have to manage congestion on the system. Typically, when we talk about congestion, that was historically driven by high demand centres. So there'd be a high demand on the network, which the transmission and distribution system didn't have the capability to deliver the energy to where it was needed. Increasingly, we're seeing that congestion driven by renewable generation. So we have a lot of generation at certain points on the network, but the consumption is coming off the network at a remote point, so the demand centre in our towns and cities, and we have to transmit that energy from where it's generated to where it's needed. So we see constraints happening as a result of that high renewable generation, leading to renewable energy being curtailed. So we need to mitigate that and find ways to not effectively waste that energy by curtailment, but to find either the way to transport it or to consume it. Okay, talk about system inertia, and we're seeing system inertia reducing fairly significantly. If we consider a fossil fuel power plant, that's a huge synchronous machine connected directly to the grid, and it's a rotating turbine. So that huge spinning mass that we have in those turbines carries a huge amount of inertia, which can help stabilize brief disturbances on the grid. On the other hand, when we think about renewables, these are connected to the grid through power electronics. Power electronics are now asynchronous machines, so they don't carry that same physical inertia that a traditional large generator would. You might expect a large wind turbine, and particularly these sort of huge multi-gigawatt wind turbines that we see connected, being connected offshore. So it's like multi-megawatt. You might think that the spinning blades in those turbines would carry a large amount of inertia. But of course, because the speed of the wind varies, so does the speed that the blades rotate at. So they have to go through a DC link, and there's then a converter to change that DC into AC to synthesize a 50 Hertz grid frequency and to synchronize and connect to the grid. Similarly, solar PV is native DC technology. So again, that has to go through an inverter to synthesize that 50 Hertz frequency and synchronize and connect onto the grid. So again, that doesn't carry that same inertia that a traditional generator would. So I've mentioned inertia a number of times there, but what is it and why does it matter? So if we go back to our GCSE physics, according to Newton's first law, inertia is the resistance of an object to a change in its motion. So in this example, the motion that we're talking about is that rotating mass of the large synchronous generators. And that's storing energy through that rotating mass, which is spinning at the same frequency as the grid. And when we refer to power system inertia, that is simply the sum of the multiple large generators connected onto the system. So there's a huge amount of inertia carried there. So that effectively acts as a sort of a shock absorber, and that slows down the rate of change of frequency when for example, a generator trips out or a large load is switched on. And so the grid has to constantly adapt to these changes in supply and demand, and as it does so, the frequency will fluctuate. So if we have more generation than we have demand on the system, we start to see the grid frequency rise. And conversely, when we have more demand than supply, then the grid frequency starts to drop. So the grid operators have to take action continuously to match that supply and demand in real time in order to maintain the stability of the 50 Hertz grid frequency. So this slide is considering some of the challenges that the system operators face. And actually, we had quite a good example recently during lockdown when there was a huge slump in demand. And actually, the UK electricity demand went down by 17% during that first lockdown in 2020. So that caused some significant concern for the electricity system operator, who sought enduring powers from Ofgem to actually be able to disconnect generation, and they were granted those powers. As it happened, they were able to mitigate and manage that reduction in demand and reduce generation accordingly without resorting to the emergency powers that they'd been granted. But it did put quite a severe test on the system to match that reduced time, because coincidentally, and if you remember back to that first lockdown, it was quite windy, and also it was beautiful sunny weather. So not only did we have a 17% reduction in demand, but we had a big increase in the amount of renewable generation that we were producing. And that actually led to the generation mix going up to almost 56% of wind and solar. And that's significant because it does demonstrate that the system can perform in a high renewable energy mix. And that was a much better performance than had been previously predicted. So that's yes. We're speaking about the managing the system when we got too much generation versus the amount of supply. Sorry, just catch up with myself. Obviously, the opposite is also the case then. So if we have our the demand on the system exceeding the amount of generation we have, then that frequency will start to drop, and that actually is worse, because that can lead to generators tripping out, and that can cause a cascading failure and ultimately a complete GB system-wide blackout. I think it's clear that we don't have enough frequency regulation on the system, and it's not fast enough to manage these changes in frequency that are happening with this low inertia system that we have. So we see a need for greater reserves of things like battery energy storage and rapidly dispatchable loads. To illustrate that on this side, and this is showing an example of how low frequency limits were breached. So I'm sure many of you are familiar with engineering recommendations G98 and G99 that are published by the Energy Networks Association, ENA. And EREC G98 and G99 set limits for, well, amongst other things, grid frequency, and there's upper and lower limits. So if we have more demand than supply, our frequency goes up. We can breach the G99 set point limit for over frequency, which will trip our generator out. And likewise, more supply than demand, we can breach the G99, G98 low frequency set points and trip our generator out. This is an example of that happening. So this probably needs a little bit of explanation on this slide. So this was an event that occurred at about 5 to 5 on the evening of Friday, the 9th of August in 2019. And this line that we're looking at here is the grid frequency measured on the electricity transmission system, on the GB system. So we see it, the timestamp here, 1652, and we see a number of almost concurrent generator trips. And so we start to see the grid frequency drop until we get down to this point. And at this point, National Grid start responding. They start calling upon all of the frequency response resources they have at their disposal, which incidentally included 475 megawatts of fast-acting battery energy storage. And those actions, we see the frequency start to rise. They start to restore the system to within, coming more towards within tolerance. But then we start to see another generator trip. That then has consequential trips as we start to see that frequency reduce, and we start to see embedded generation tripping. We start to see larger generators tripping because we're going below those low frequency grid set point limits as dictated by G98 and G99. And the frequency drops all the way to this point here. This is 48.8 hertz. And when the frequency reaches that point, National Grid instruct the distribution system operators to do something they call LFDD. And that stands for low frequency disconnection of demand. And that is in fact an indiscriminate shutdown of the distribution network. This issue occurred in the southeast, so UKPN started shutting down their distribution network, effectively plunging consumers in the southeast of England into the dark. Now that sounds like a very draconian measure to take, but if they hadn't taken that measure, then this frequency would have continued to decline, and we'd have then had that cascading failure throughout the GB energy system, and we'd have had a complete system-wide blackout. So it was a draconian action, but we can see once those supplies are disconnected, we can see the grid frequency fairly quickly come back up to within tolerance limits. And if we look at this timestamp, this is 1657. So just under 5 minutes end to end for the transmission system frequency to start dropping, actions to be taken to restore that frequency, and for it to come back within tolerance. So a very short duration event. The impact was felt a little bit longer than that on the distribution system. It took about 45 minutes for the distribution system operators to restore all the supplies on their network. But there was a tremendous amount of media coverage of this event, not just because of the power cut, but because of the impact that had and the knock-on impact it had. For example, the exposed hospitals that didn't have appropriate backup generation controls in place, exposed weaknesses in the transport sector, in particular on trains. And it was found that some trains were unable to reboot after this event. And so the rail operators had to send engineers out onto the rail network to physically go and reboot these trains. So we had commuters stuck across the southeast of England. And bear in mind, this was just before 5 o'clock on a Friday night. So there'd been a lot of commuters in the southeast of England trying to get home for the weekend, and they were stuck on the train for over 9 hours in some instances. So there was, as you can imagine, a very big post-mortem of this event. And this slide is actually taken from the post-event report. And if any of you were involved in the accelerated loss of mains change protection event, that was driven by this occurrence. And the Energy Networks Association determined that where there were consequential renewables and embedded generation trips, very often it was driven because of using vector shift frequency sensing. And so the accelerated loss of mains change protection demanded that all generator protection relays were changed to what they call rock-off, which is rate of change of frequency sensing, to try and prevent these events happening in future. So I think I've spent quite a bit of time on that slide and explained it in some detail. I think really the key takeaway from this is that fast-acting flexible energy resources are absolutely critical to maintaining the operation of the power system. And clearly we didn't have an adequate amount of resource when this event occurred in 2019. And as we have higher renewables penetration, as that system inertia reduces, it will become imperative that we continue to increase the base of flexible energy resource that we have that has the capability to respond very, very rapidly. So I've talked about flexible energy resources there a fair bit, and we've got a quotation here. This is from a Bloomberg New Energy Finance report, and they stated that the energy transition will be faster and less costly if flexible energy technologies and energy markets become the cornerstone of the grid. We've explained the flexible technologies, but why energy markets? That's because there has to be a driver for consumer behavior. So we need those energy markets so people can get rewarded for taking action to install and to use flexible energy resources. And we start to see a much greater variability in the demand on our electricity network as we increase the amount of electric vehicles and heat pumps that we start installing. And of course, we see a greater variability in supply as we increase the amount of renewables on the system. So we need to be able to find ways of matching that variable supply and that variable demand. And that's through using flexible energy technologies. So some of the sources of flexibility that we see, the first one and a traditional one is demand side response. And this is where consumers have the ability to rapidly alter their electricity usage in response to an external third-party signal, so they can better match the needs of the grid during system stress events. And so when we've talked about traditional demand side response, this has just simply been reducing or increasing site load according to the network needs. But as we see that growth in behind the meter generation, we can also see response actually being to export energy from on-site renewables. So a building can in effect deliver a net negative demand to the system to help manage that system stress event. The next source of flexibility we're going to talk about is interconnectors, and this enables the system operators to effectively manage the import or export of power over a wide geographical area, so effectively between countries. So therefore you might have one country which has a good wind and solar resource at one time when another area doesn't. So we can move that renewable energy geographically around. Here in the UK, we currently have a total of 7.4 gigawatt of interconnectors. That's made up of 3 gigawatts to France, a gigawatt each to the Netherlands and Belgium, 500 megawatts each to North and South Ireland. And just fairly recently went live is the North Sea Link, which is a 1.4 gigawatt connection to Norway. We've got a further 6.1 gigawatts of interconnection in the planning, so a significant amount of capability to move electricity. And some of you may have read about reports of even having a hardwired interconnector to access the ample solar resources in Morocco. So actually linking all the way out to North Africa where they have that solar resource. Then move on to talk about energy storage, and energy storage comes in many different forms and guises. So we're mentioning a number of technologies here. The first one, PHS, that's pumped hydro storage. So that's your traditional hydroelectric power system where you have a high level reservoir, a low level reservoir, a dam holding that water back, and then we release the water through the dam. So it drops down through gravity and spins a turbine and generates electricity, and the water flows into the lower reservoir. And then we reverse that process when we have energy available again. So that pumped hydro storage, very effective, been used for decades and decades. Quite difficult to expand though, because it requires a very, the right geology in the area to deliver pumped hydro. So not a great scope for increasing the pumped hydro resources. The next two, CAES and LAES, are compressed air and liquid air energy storage respectively. Compressed air is a fairly nascent technology. This is where we have the capability to pump air into underground caverns, and typically that's where we've already extracted oil and gas. So there's huge underground caverns that we can effectively pressurize air in and then release that air again to drive a turbine and generate electricity. Similarly with liquid air, this is a cryogenic store. So this is a land-based system where you hold air in liquid form at very high pressure and low temperatures, and then you release that again to drive a turbine and generate electricity. We have flywheels as a means of storage, similarly actually to the inertia that I was discussing in the power system. But for anybody who's familiar with a rotary UPS, for example, that's a spinning flywheel to store energy. We have supercapacitors. They have capability to charge and discharge very large amounts of energy very, very quickly, but over short durations. And of course, we have battery energy storage, which typically operates over the sort of the 1 to 4 hour duration. One thing that's absolutely critical is that last comment about having energy storage resources available to meet demand over various timeframes. When we're talking about frequency regulation, we're talking about millisecond response timeframes that we need. But when we talk about things like days and weeks where we have low solar or low wind resource, then we need that things like that compressed air energy storage, large scale, long duration energy storage. And that's really an area for significant research and development to bring that on to really help us integrate those renewables and help us to use that power when it's being generated and to deliver it when we need it to consume. Some other sources of energy storage that we can talk about. I haven't talked about thermal storage, but don't forget thermal storage. Of course, that can be our basic immersion heater. It can be molten salt. It can be things like ground source heat pumps, effectively a means of thermal storage. And we have things like power to gas. So that might be an example, such as using electrolysis to make hydrogen. Power to heat, something like a heat pump or an electric boiler. We have smart charging, and that's been mandated in the electric vehicle smart charge point regulations, which came into force in the UK last year. So that can help provide flexibility. And one technology which has a huge potential capability in flexible energy resource is, it says V to G here, vehicle to grid, but that's often replaced now with V to X, so vehicle to anything. It might be vehicle to load, vehicle to building, vehicle to home, vehicle to grid. When we think about the amount of energy in our vehicles, in whatever form that's stored in, mostly today in a liquid fuel source, but when we have that density of battery electric vehicles, there's a colossal amount of energy sitting on our drives doing nothing most of the time, or sitting in our workplace car parks. And that, if we can access vehicle to grid, that has huge potential to provide energy flexibility. So move on to battery energy storage in a little bit more detail. And I think really it does what it says on the tin. It enables us to store energy when it's available, and then we can release it to service our demand when we need it. It can go in a wide variety of locations, in our homes, in our businesses, or in an industrial scale, connected directly to the utility at a megawatt scale. So this slide is just illustrating some of the use cases for each of the various potential user groups of energy storage. And so it really applies in all situations: residential, commercial, industrial, and transmission distribution level. I'm not going to go through each one of these thumbnails, but broadly these drivers break down into 5 different categories. So the first is saving money on electricity and operational expenses. We have optimization of renewable energy resources. We have the capability to defer utility system investment to mitigate the need for grid reinforcements. We have the capability to maintain system resilience by providing backup power and by providing those flexible resources to manage the grid system. And we can use the systems to generate revenue from providing grid ancillary services. This slide is just illustrating sort of, I suppose, a stylized single line diagram illustrating how a battery energy storage system would integrate into a commercial building system. So effectively, so we've got our utility supply here going through our smart meter. And this line along the bottom is just representing the AC power distribution system within a building. So we've got our loads connected to that power distribution system. We've got our generation here illustrated as solar PV, which in the majority of cases in the built environment is solar, but we do see wind and we do see other renewable technologies in the built environment. So that's going through our inverter and feeding energy, either to support our building loads, whether that's EV charging our battery, or direct loads, or potentially exporting that back to the grid. We've got our electric vehicle as represented here as a load to the building. So that's taking energy, say, from our solar or from the utility to charge our vehicle. And when we enable vehicle to grid, that might become bidirectional. We have our battery energy storage. This is now a bidirectional connection. So we can take power from the grid to charge our battery, from the solar, and of course we can discharge it to feed our loads to charge our vehicles. Theoretically, we can discharge it to export back to the grid, but realistically, there's no good commercial case for doing that. We wouldn't want to export from storage to the grid. We'd want to use that stored energy to support our building demand. We've also got our backup power illustrated here. We're showing it charging a vehicle, but it could be any critical service that you wanted to support through using your battery energy storage effectively as a sort of a UPS system. At the center here, we've got the application controller. That's the brains. This is the digitalization piece here. This is where we program all of the various functions to manage those use cases. And so the yellow dotted lines represent the flow of data that we've got around the system from the metering and the management of the overall system. This is a summary of those different value propositions from using energy storage, and I'll explain each of these in a little bit more detail on the following slide. But broadly, it boils down to enhancing green credentials, building system resilience, enabling us to optimize our renewable energy resources, to manage our energy and generate system revenues, and to integrate on-site loads. Talk about electric vehicles here, but it could be any increase in site loads. Just to explain the little image we have on the right-hand side here, that's our X-Storage compact system. It's an all-in-one system. We see a single rack here. This is up to 40 kilowatts, 50 kilowatt hours in this 600 by 1000 footprint. We can add a second rack with a second or third string of batteries in, so that would become 40 kilowatts, 50, 100 or 150 kilowatt hours. And then we can parallel up to 5 power converters, each of which can have 1, 2 or 3 50 kilowatt hour battery strings attached to it. So up to 200 kilowatts with 250, 500 or 750 kilowatt hours of stored energy capacity. Okay, talk about these different modes of operation here. So this is, first one is renewable energy integration, illustrated here as PV, and we're illustrating it as a domestic use case. This profile would be typical of a residential application, but it also would be equally applicable in a commercial environment. So basically, wherever we have a greater amount of on-site renewable energy generation than we have site demand, then we would either have to export or curtail that energy, or we can store that energy. So we're illustrating here that this is effectively a sort of stylized version of a demand from a residential home. So we see in the morning we've got a little bit more demand for breakfast, we've got a lunchtime increase in demand, and then we come home in the evening and we turn the telly on and we start cooking our dinner, so turn the lights on, so we've got more demand in the evening. But our solar generation follows this typical bell curve with the peak at midday. So if we can charge our battery with this piece of energy here, then we can defer that energy and fill in effectively under the curve here. So we're utilizing that zero carbon energy from our solar PV in preference to importing energy from the grid. So clearly there's some cost benefit to do that, and clearly there's some CO2 reduction benefits to doing that. Next one to mention is backup power. I think that's fairly self-explanatory. Effectively, you can use your battery to provide power to critical systems during a power outage. Next one, I should have said on the previous slide, actually, that integration of solar PV particularly is the #1 driver for installing battery energy storage systems in the built environment. #2 is peak shaving. So this is where we have an increasing building demand that would require us to otherwise upgrade our building supply capacity. So we might need a a transformer upgrade, we might need cables reinforcements, we might need upstream reinforcements, and we can use a battery energy storage to help mitigate that by charging the battery when we have lower building demand and releasing that energy at those times when the building demand is peaking and putting a strain on our supply capacity. I had an example of this project recently. It was a large supermarket. They could only get a 250 kVA supply from their local DNO. To get a large supply required grid reinforcements up to 132,000 volts, and irrespective of the colossal cost of that upgrade, they couldn't do it before 2030 at the earliest. They had a forecast store demand of over 300 kVA, 250 kVA grid supply, so battery energy storage was able to mitigate that and provide that additional 50-60 kVA that they needed during their store trading hours. So peak shaving is quite a common application. We then have load shifting. This is basically just changing the time at which you consume electricity. So for example, if you have a day-night electricity tariff differential, a lower rate overnight, typically midnight to 7 AM, you might choose to charge your battery at those lower price periods and then release that energy when your cost of electricity would otherwise be higher, so you can exploit that delta. And that might also be the case if you have an energy tariff, for example, where you have the distribution user system charges passed through, which are typically highest in the late afternoon, early evening period. So you might use your storage to support your building loads, for example, from 4 PM to 7 PM. We spoke about frequency regulation in quite some depth earlier, so I won't go into too much detail here, but this is just illustrating how the storage system can monitor the grid frequency and then automatically charge when the frequency is increasing. So we effectively add a load to the system to take some energy off and help manage that increase in frequency, and discharge when the frequency drops. So we support that imbalance between demand and supply on the system. This slide is actually a study that was done in a report commissioned by Eaton and Statkraft, and it was authored by Bloomberg New Energy Finance. And they were looking at the impact on the transmission system and distribution system based on a fairly deep adoption of electric vehicles. And this was based on 50% of households owning an electric vehicle. And what the conclusion of this study found was that on the transmission system, there was a relatively limited impact. It's about a 15% increase in electricity demand as a result of half of all houses having an EV at a transmission level. So whilst that's a reasonably substantial increase, it's not problematic for the system, because we've seen bigger reductions than that as a result of energy efficiency savings over the years. So we've actually released grid capacity, and particularly through things like the introduction of LED lighting, that's released capacity on the transmission system. So there's plenty of capability for that amount at that point in the system. But of course, adoption of electric vehicles and heat pump technologies isn't going to be spread uniformly around the country. There will be hotspots where we see faster adoption. And here we see a much deeper impact on the distribution system, where we might see an increase in demand of 30 to 40% if that load is left unmanaged. So that's going to present a massive problem for distribution system operators, and has the potential to lead to very expensive and potentially unnecessary overbuilding of the distribution system. So managing electric vehicle charging is absolutely critical to prevent that overbuilding and that cost being incurred. So that will be achieved partly through the mandated smart charging regulations. As I mentioned previously, the electric vehicle smart charge point regulations did come into force last year. So we have to have things like random delays on when we charge. By default, we have to charge overnight in off-peak periods. So that will help manage. It will also, vehicle to grid will help manage that as we adopt that. And we also see what we call non-wires alternatives to grid reinforcements. And this is illustrating what I mean by non-wires reinforcements. So it's effectively a peak shaving application. And we're illustrating here how we can use battery energy storage to support that increase in vehicle electrification. So where we want to add EV charging infrastructure to our building, we reach a point where we can't add any more without having to upgrade our supply infrastructure. So if we use a battery, we can use that to say charge up when the demand on the building is lower, and to release that energy when we see additional vehicles plugging in to charge up. So effectively, we're managing that power within the building and not having to increase that supply capacity. Okay, so this slide just really summarizes that. So hopefully we've demonstrated how, through the use of on-site renewable energy resources, through battery energy storage, through flexible EV charging capability, we can help control our energy supply, we can manage our electricity bills, we can improve our overall building sustainability, we can mitigate grid supply interruptions by providing backup power. So we increase the system reliability, we reduce our dependence on the grid infrastructure, and we through using these technologies, we can harness the full potential of all of our renewable energy resources, particularly those in the built environment, but also those on the wider grid infrastructure, by using the system to help manage those, for example, frequency imbalances, delivering those grid ancillary services. Okay, so that draws me to a conclusion now. I'll hand back to the moderators if there's any questions.
Thank you, Richard, for this informative presentation. We actually do. So I'll start with the first one. What is the efficiency and/or losses in an average battery storage system?
Yeah, it depends where you look. The converter efficiencies are typically 96, 97%. But there are what we call, the way we really usually look at this is what we call round trip efficiency. So in other words, if you put 1 kilowatt hour into a battery and then deliver that energy back out to a load, how much do you get? And typically you see it around about 85 to 90% round trip efficiency.
Thank you. Another question and comment. What developments do you see in the future in batteries, and how long before current lab developments hit the market? For example, higher energy density and hence physically smaller units for the same storage, lower risks from battery damage or failure with different technologies.
Good question, yes. Yeah, there is a huge amount of research and development into battery, well, into all forms of storage technology, but particularly battery energy storage. And of course, battery energy storage takes a wide range of forms. I think the question is probably specifically talking about lithium-ion energy storage, but of course we shouldn't forget traditional lead acid. There's other battery technologies such as redox flow batteries. And we're seeing, as I say, a lot of research and development into this area for different timescale storage periods. But if we just focus in on lithium ion, probably the two dominant chemistries, I say, lithium ion is an umbrella terminology which covers a wide range of different sub-chemistries. And probably the two dominant chemistries that we see today are NMC, that's nickel, manganese, cobalt, and LFP or LiFePO, which is lithium iron phosphate. NMC is currently the most commonly used in battery electric vehicles because it has a high energy density. It does have more concerns over fire safety through thermal runaway, although that can be managed and mitigated with good battery energy management systems with appropriate technology and physical construction of the battery. But we are seeing more and more applications using LFP. So for example, if we talk about Tesla, their long range vehicles use an NMC chemistry, but the Model 3 standard range is now using LFP, which has a much higher thermal runaway point and is considered generally a safer technology. We see talk about things like sodium ion, which won't burn. And I think what's often talked about in the battery storage technology forums is solid state batteries. So that's where we move from having a liquid electrolyte to a solid electrolyte. And that will allow very significant increases in energy density. So there's two ways that can benefit, either in the same size and weight of battery, we would have a vehicle that could travel significantly further, or a storage system that could deliver significantly more energy, or it will enable us to reduce the size and weight of those battery packs to improve efficiency and to reduce costs. And actually we'll probably see both of those things happening. I think we're still probably a few years away from solid state technology. It's happening certainly in the lab. but will probably be the next breakthrough technology. And we shouldn't forget, of course, we see incremental improvements in all of the battery chemistries as we go on. So energy density, life cycle expectancy, and so on is improving all the time. Hopefully that's answered that caller's question.
Yeah, thank you. Another question, what's the end of life strategy for batteries currently being used?
Yeah, another good question. As a producer of batteries, anybody who places batteries onto the market is obliged to offer a recycling service for those batteries. The type of service and how far that obligation extends depends upon the nature of the battery. At Eaton, as a battery energy storage manufacturer, that is classed as an industrial application. So we are obliged to provide a recycling service for those batteries at end of life. I think it's an area where we'll see a lot of development. I think there is a relatively low capability for recycling in Europe currently. Most of the capability exists in China. We're starting to see vertically integrated battery manufacturers who are doing that recycling, recovering the vast majority of resources from those batteries, and then reusing that resource in new batteries. And we'll see that increasing. I think there is now a lithium-ion recycling facility in the UK, but we do really desperately need to see an increase in that. But I think one thing that perhaps is reassuring is we do have the capability in the technology to recycle these batteries, to take that all of the materials in there and to reuse those. And now, of course, they're a valuable resource, and we really want to focus on that circular economy, so taking back that those minerals. And I mentioned NMC. There's a lot of talk about cobalt, for example, and a lot of talk about the supply chain for cobalt. So we need to make sure that we reuse that where we can, or move away from it as time goes on, the chemistries improve. Okay, is there another question?
That's all for now, but if attendees have any more questions, they are free to send us an email to marketing@rexel.co.uk. So please feel free, and then we will send them to Richard and get back to you. Also, as mentioned earlier, your CPD certificates will be sent directly from CPD. It takes 4 to 5 weeks from today, so bear with us. And we will have another webinar with Eaton in December, so watch out our socials for more details. I think that's all for now, and thank you again, Richard, for your presentation, and thank you everyone for attending, and see you soon.
Thanks very much, everybody.